Hello everyone, and welcome to my channel. This channel is an educational channel. We look at some great theories of everything and go deep into them, try to flesh them out and see how we can benefit from them. Today is our 475th video on the reciprocal system of theory from one Dewey B. Larson. And in 1959, Larson proposed his two fundamental postulates. Just two sentences about how he believed the universe operated. From there, he went through a process of deduction, and if this, then that type of approach to arrive at his theoretical universe, what the universe would look like if his postulates were correct. And then in this book, particularly, this book that we're looking at today called Basic Properties of Matter, Larson compares his theoretical universe with the empirical measured universe of the legacy scientists. And in this book, he's looking at this in terms of chemistry. So Larson arrives at the equations for many of the basic properties of matter, like the melting point or the compressibility, and then plugs in all of the elements on the periodic table and many compounds, and compares them to the scientific tables that have already been published. We're looking at chapter 8 of this book that's called temperature relations. Now, Larson's two postulates articulate, the first one is really his conception of the universe, and then the second one is kind of the conception of the universe that most scientists hold, that really is almost a prerequisite for them being scientists, although there are exceptions. But he basically uses the second postulate to flesh out his theoretical universe from that first postulate. So the first postulate is that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. And then the second postulate is just that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. Now, there's a lot of people, some of whom are in Larson's, sphere of associates. Larson died back in 1990, but the group that he formed and the journal that people wrote, the very few people who know about this, many of them actually disagree with the second postulate in their particulars, in the particulars of Euclidean geometry and in commutative mathematics, and are looking at more 20th century types of math and geometry, which is, I actually agree with that, but I don't think it's really that important at this point. What we're really trying to do is look at that first postulate. And there are really 4 prongs of the first postulate. The universe is made out of motion. Motion is the relationship between space and time. That sets up basically a reciprocal relationship between space and time. Motion is made out of space and time. And then space, time, and motion come in 3 dimensions. Space, time, and motion come in discrete units. Now, I'm going to try to shorten this up here, but and maybe try to get into some of the details as we get into the reading a little bit. if you want more, you can go to any of my previous 474 videos on this subject, and I've gone through a fairly detailed explanation of the reciprocal system. But you know, we're just not making enough progress getting through the reading because it takes a very long time to explain all the relevant details of the reciprocal system. But basically, when Larson is referring to motion, he's not the first, but one of the few who attempts to construct this universe on motion, not matter or energy or something like that. And when Larson is referring to motion, he's really referring to what he calls a scalar motion. Scalar motion is a motion that has a magnitude, but it has no specific direction. And you can model the scalar motion using a balloon that you put dots on. If you blow up the balloon, all of the dots will be moving away from each other. On the expanding surface of that balloon, every dot will be moving away from every other dot. And even the locations between the dots will be moving away from one another. So basically, all of the dots are moving in every direction. There's no specific direction. And the same is true if you contract the balloon and it goes in, all of the dots will be moving toward each other. And again, they won't be moving in any specific direction. They'll really be moving in every direction. Larson refers to these as the progression. The outward motion is the progression, and the inward motion is gravitation. And gravitation is basically an artifact of matter. Whereas the progression is really the source of everything. This is Larson's internal motion, his 0 point motion. The state of rest of the universe is to move outward at the speed of the progression in all directions, at all times, in all locations. Okay, so this is the omnipresent universal force of the progression. And it proceeds at the rate of 1 unit of space per 1 unit of time. And this is from the discrete unit postulate. Everything has to be in units. You have to have a full unit of space before you have space, and you have to have a full unit of time before you have time. And really, space and time don't even have a independent relationship. They only exist together in motion. And the motion of the progression is 1 unit of space per 1 unit of time, outward, in all directions, from all locations, at all times. And that is the empty universe of Larson, the state of rest. And then manifestation occurs by basically kind of rolling back that outward motion of that balloon and turning it into the inward motion of gravitation. Since the progression, since motion has 3 dimensions, it has to be rolled back in 3 dimensions. And really, first it gets neutralized and then it gets rolled back. And the first thing that will start to neutralize it will be the photon, and then the photon gets rotated to become a particle, and then particles combine to become atoms. And so the atom has 3 numbers in Larson's system. This is basically his periodic table. And one is a 2-dimensional rotation. Another is another 2-dimensional rotation, a secondary 2-dimensional rotation. And then the third is an optional 1-dimensional rotation in the opposite direction. So those are the 3 numbers that Larson uses for every element. And he plugs those numbers or permutations of them into his equations for the basic properties of matter. Now we're going to just try to read from there. There's a lot of other stuff about the reciprocal system, but many of those things may come up while we're going through this. Now, he was talking about temperature relations, and we were looking at the coefficient of thermal expansion. And he was going through various elements. He determined that this 3,576 degrees is like the maximum melting point, or the maximum end of the solid state. And then which is just like everything else in the reciprocal system, is quantized. It's based on levels in discrete units. It's not a continuum, but it's got levels, and there are different levels of your coefficient of expansion. That's one major thing about the reciprocal system that is different than legacy science as far as temperature is concerned. In legacy science, temperature is part of the aggregate of matter. You take the aggregate of matter and you can take its temperature. In Larson's system, the temperature is the property of an atom, of the atom. And then an aggregate is really just the average temperature of all of the atoms in the aggregate. And so so the melting point, for example, is reached when a certain percentage of the atoms are in the liquid state. It doesn't have to do with the whole aggregate becoming a liquid. It's a percentage. I think it's like something like 30% approximately of the atoms need to be liquid before the whole thing becomes liquid. And what really happens is that not the chemical bonding, but the geometric bonding of like an aggregate of matter will, the crystal lattice will be broken apart when a certain percentage of the atoms are no longer in the solid state. And so the whole thing just kind of collapses at a certain percentage. But just keep that in mind, that the state of matter is the result of the atom, not of the aggregate in Larson's system. Okay, let's just start reading and we'll see where we go. The effect, and again, we're just trying to glean a few things at a time, some breadcrumbs, and learn just a little bit more about the reciprocal system. You're not going to be able to pick up the whole thing here because he gets into a lot of detail that, is probably a little bit too advanced certainly for a beginner. It's too advanced for me, and I've been studying this for a while. I'm still trying to figure out what he's talking about half the time. So, but when I do figure it out, it buttresses me to keep studying it, because once I figure it out, I'm like, oh, there really is something to that. He's not just like talking out of his elbow. He really does have something that he's trying to express, but sometimes it's just too difficult to get to. So you just have to be happy with a little progress at a time. Okay, the effect of the difference between the solid endpoint and the melting point can also be seen at the 3-unit level, as the melting point ratio of silver, 3576 over 1234, which is 1234 is the melting point of silver, which equals 2.90, is raised enough by this difference to put it over 3. So he's basically saying that the solid endpoint and the melting point are not the same. There is a gap between the solid endpoint and the melting point. That's because the levels of temperature in the liquid state are quantized. So there's no continuity. An atom in the liquid state cannot take any temperature. It only can take certain levels of temperature. And so once it crosses get past the solid endpoint, it's not automatically a liquid until it reaches that next level of temperature. And there's a gap. So when we say that the melting point of silver is 1234 degrees, the endpoint, the solid endpoint, is a point that's lower than that. And that is enough to allow silver to get to the third level of the coefficient of thermal expansion, which is 15.5 times 10 to the minus 6 per degree Kelvin. So silver then has the 3-unit 15.5 times 10 to the minus 6 expansion coefficient at the upper initial point, as shown in the upper curve, figure 14. At the next unit level, the element magnesium, with a ratio of 3.87, is similarly near the 4.00 mark. But in this instance, the endpoint increment is not sufficient to close the gap, and magnesium stays on the 3-unit basis. None of the elements for which sufficient data were available for comparison with the theoretical curves has a melting point in the 4-unit range of 715 to 894 degrees Kelvin. But since the magnetic rotation is limited to 4 units, and the magnetic rotation, that's the 2-dimensional rotation that makes up like the A and B numbers in the periodic table for Larson. But since the magnetic rotation is limited to 4 units, the 4-unit initial level also applies to the elements with melting points below 715. This is illustrated in figure 15 by the curve for lead, melting point 601 degrees. As can be seen in figure 14, the expansion coefficient of silver, as measured experimentally, deviates from the straight line relation in the vicinity of T1, that is the first transition temperature. This deviation is not due to experimental error or to structural readjustments. It is a result of the nature of the transition from the 1-unit expansion below T1 to the multi-unit expansion above this temperature. Unlike the specific heat transition, where the increments represented by the second segment of the specific heat curve add to the specific heat at T1, the expansion represented by the second segment of the expansion curve replaces the expansion represented by the first segment. So this is the specific heat is kind of like the efficiency of heat addition. Like when you add heat, how much heat do you have to add to something to raise it by a certain temperature? And a couple chapters ago, he went through all the ins and outs of the specific heat. And now, so he's comparing basically the dynamics of the specific heat curve with the dynamics of this thermal expansion curve. And so unlike the specific heat transition, where the increments represented by the second segment of the specific heat curve add to the specific heat at T1, the expansion represented by the second segment of the expansion curve replaces the expansion represented by the first segment. So that's a difference there. The thermal expansion curve replaces the first segment as opposed to adding to it. The initial level of the second segment at 0 temperature is the unit or N unit level reached at the end of the first segment. I'm almost getting that, but not quite. This means that at T sub 1, the molecule undergoes an isothermal expansion to the level of the second segment at that temperature. In the aggregate, the individual molecule expansions, molecular expansions, are spread out over a temperature range by the distribution of molecular velocities, and they appear as a bulge in the expansion curve. Coincidentally, there is a downward deviation in the curve similar to that of in the experimental specific heat curves due to the effect of the transition to the more nearly horizontal second segment of the curve. The net effect of these two types of deviation from the theoretical curve applying to the single molecule depends on their relative magnitude and on the temperature range over which the deviations are distributed. The curves of Figure 14 have been selected from among those in which the net deviation is at a minimum. In order to minimize uncertainties in the definition of the upper sections of the curves and to make it clear that these linear sections actually terminate at the calculated initial levels. More commonly, the bulge is quite pronounced, as in the curves for gold and lead. Okay, now just remember that while we're you're heating up a solid, Larson bases a lot of things in his system on probability. That's part of the second postulate. The universe conforms to the relations of ordinary commutative mathematics. And so when Larson figures out his deduction, when he deduces his theoretical universe, he uses probability to determine what can and what can't exist. And what can exist is always what is most probable. And in Larson's system, the solid is more probable than the liquid. And so the atom is going to do everything that it can to stay in the solid state, even when it is heated up. And so it goes through various gyrations, like making transitions from one rotation to another rotation in order to slow down its progress toward the melting point. And so you can see this in the specific heat curves, that it tries to kind of minimize the amount that it approaches the melting point by kind of raising its specific heat, so that you have to pump in a ton of heat to move it toward the melting point. You end up raising the temperature by a lot, but you don't move it anywhere closer to the melting point. So those are one of the kinds of transitions that an atom will go through as it gets heated up. The other is really an adjustment of its geometrical structure, or its crystal lattice, from say the hexagonal Coulomb packing to the tetrahedral arrangement, or something like that. Now, we were talking about these two different transitions that an atom is going to take as it gets heated up. Kind of losing my train of thought here. Just keep in mind that the solid state is more probable than the liquid state. The solid state is when an atom is in what Larson calls the time region in 3 dimensions. And the time region is the region of less than 1 unit of space. Because if you don't have a full unit of space, then you don't have space because of the discrete unit postulate. You have to have a full unit before you have anything. And so if two atoms approach each other to one unit of space, which is approximately 2/millionths of an inch, then they can't get any closer in space. So what they do instead is they move outward in time, because time is the reciprocal of space. And so moving outward in time is equivalent to moving inward in space. And so they really move outward in time, but we see it as inward in space because we are creatures of the spatial reference system. Larson bases a lot of things on the reference system. Okay, so the spatial reference system is when we are anchored by gravity or by gravitation to the spatial reference system, which is basically 3 dimensions of space. Just the normal reference system that we're accustomed to living in, where we've got space is still and 3-dimensional, and time is progressing. Time is always getting later and later and later. But there is also, by the reciprocal postulate, theoretically a place in the universe where there would be 3 dimensions of time in a still frame, where time is still and space is progressing. So Larson refers to that as the temporal reference system. And that is the inverse or the reciprocal of the spatial reference system. These are both stationary reference systems. Now, the progression is a moving reference system. He calls this the progression of the natural reference system. And this is the motion at 1 unit of speed. 1 unit of speed is 1 unit of space over 1 unit of time. And so there is a time region within what Larson calls the material sector that is subject to this spatial reference system. And then there is a space region in the cosmic sector, which is the inverse of the space region, of the time region. And this is where particles, cosmic particles and cosmic atoms approach each other to the point where they're 1 unit of time apart, which is approximately 10 to the minus 16 seconds. And when they can't get any closer in time, then they move outward in space, which is the equivalent of moving outward in time by the reciprocal postulate, and seen by denizens of the cosmic sector as still moving in time, closer in time. So, this is just kind of building up the architecture of, the reciprocal system landscape. And so we have this natural reference system, and then we have a spatial reference system and a temporal reference system that are stationary. And so even though the scientists use this spatial reference system, it is very limited. You can have 3 dimensions of space in the spatial reference system, and you can have 3 dimensions of time in the temporal reference system, but you only need 1 dimension of motion to express all 3. And you have 3 dimensions of motion. And so these reference systems, these stationary reference systems, are not sufficient to describe what's actually going on in the universe of motion. And I guess that's where Larson is using this natural reference system, the moving reference system, to make his measurements. He makes his measurements from the moving reference system. Okay. There's a lot of stuff I'm missing here, but let's keep going. When the effect of the systematic deviation from the linear relation in the vicinity of the transition point is taken into consideration, all of the electropositive elements included in the compilation of expansion data utilized in the investigation, except the rare earth elements, have expansion curves that follow the theoretical pattern within the range of accuracy of the experimental results. So again, he's saying that, you know, my theoretical universe, the universe that I arrived at by theory, coincides with the universe that was measured by the scientists. So these scientists are using millions or billions of dollars in their laboratories to make these experiments to determine the basic properties of matter for chemistry. But Larson's able to whip up those same numbers with a slide rule in his living room that he works on at night from his day job, and with no resources and no army of scientists employed for the task. It's just him and his slide rule. And he's able to reproduce the same results that the scientists are getting from measuring it. So that is, I think, important tell about how accurate that Larson's onto something. He might have certain things wrong, but he's definitely onto something. Another thing I would say about this is that the reciprocal system is a general theory. So even though we're, kind of in the weeds here talking about thermal expansion and the like, recognize that the principles of thermal expansion also apply to astronomy, or they apply to economics, they apply to metaphysics. This is a general theory. You're not going to be wasting your time learning any subject like you might be if you were learning, chemistry, for example. What you learn, say, in graduate school in chemistry is pigeonholed. You probably can't even have a conversation with an organic chemistry person or something like that. Fields that are even close by, you guys have a totally different language and a totally different jargon or whatever. But with Larson's system, everything is intertwined. Okay, let's just try to finish this paragraph here. We're not even going to be able to do that. Okay, well, just trying to read a little bit more, but I feel like I'm leaving you even more confused. So we'll see how it goes from here. But thanks for tuning in today, and have